And that brings us to a definition of the type of bonds that we're going to generate. A sigma bond, and this is the Greek lowercase sigma, a sigma bond occurs with head-to-head overlap of two orbitals. And you can see here we've drawn an S-S overlap and an S overlapping with a P orbital. This might occur in, say, HF, where you have a 1s orbital for the hydrogen and a p orbital for the fluorine. You can overlap that S with the P, but it occurs on the axis between the two nuclei, head-to-head overlap, and that is a sigma bond. You could also get overlap of two p orbitals, and that's shown on the end. Remember that these p orbitals, that's only one of three mutually perpendicular orbitals. And if you can envision two atoms approaching each other, only one of those p orbitals is going to be able to give you end-to-end overlap. The other orbitals, say the one on the y-axis or the z-axis, those are going to approach each other side to side. So you have electron density above the axis of the nuclei and below. And that side-to-side overlap we will define as pi bonding. That's when the overlap occurs on above or below, or in the case of the z-axis p orbitals, it would be in front or behind the axis of the nuclei. Next to that, you can see a D overlap. Remember that the D is a four-lobe structure, so you have those four lobes, and you can see the two D orbitals overlapping. Again, it is not on the axis of the nuclei, so that's a pi bond. All single bonds are sigma bonds. The first bond formed between two atoms will always be a sigma bond. Multiple bonds will consist then of a sigma bond and one or two additional bonds that are pi bonds. So HCl gives you one sigma bond, no pi bonds. Oxygen over here gives you one sigma bond and one pi bond. And nitrogen that has a triple bond, the first bond formed is a sigma bond, the second two are pi bonds. So let's practice, look at the first diagram and see if you can determine whether that is sigma or pi overlap. Is it side to side? Is the overlap occurring on the axis between the two nuclei, or is it occurring above and below the axis of the two nuclei? In the second diagram, I have shown a classic organic chemistry way of writing complex carbon containing molecules, and we can count the sigma and the pi bonds in each molecule. 1, 2, 3, 4, 5, 6, 7, 8. This contains 9 sigma bonds, and there are 2 double bonds, so there are 2 pi bonds in the molecule. See if you can identify how many sigma and pi bonds are in the second molecule. I will warn you when you do this, it's very easy to forget a bond. It's very easy to forget counting a sigma bond whenever you see them. People look at this and immediately say, oh, look, I'll count the pi bonds with those double bonds. But they'll often forget to count that as also a sigma bond. It's also easy to forget this bond here. So working your way around the molecule, make sure you count all the bonds. Okay, so opposite charges attract, and this is known as Coulombic forces. If you consider the attractive forces between two ions that have a +1 charge and a -1 charge, we have this formula here that tells us that what that force is between those two ions. And it's essentially proportional to 1 over d squared, where d is the distance between the two ionic centers. If we have a similar distance but the ions involved have a +2 and a -2 charge, then ultimately F, or the force between those two ions, increases. It actually quadruples. So we can say that the force acting between two ions is proportional to the magnitude of the charge on the ions. If we go back to our 1 + 1 - charge, but now increase the distance between those two ionic centers, we see that the force decreases. So it is inversely proportional to the distance between the ionic centers. This formula down here is the one that I like to use, and just simply say the force is proportional to Q1, Q2, those are the charges on the ions, divided by R, which is the radius or distance between the two. But molecules are not ionic. They are dipole moments, and dipole moments, mu, are for a diatomic system equal to Q times D. Q is 1.60218 times 10 to the minus 19th coulombs. Remember, coulombs is our unit of charge. The distances are very small because we use the Debye unit. A Debye unit is 1 Debye is equal to 3.336 times 10 to the minus 30 coulomb meters. And the distance between the distance between atomic centers is in the order of picometers. So they're very short. So the units for this are very, very small. This is the theoretical calculation of the dipole moment. And from that, we can measure the ionic character. Remember that I told you when we talked about deciding whether a bond was polar covalent or ionic, we could look at the difference in electronegativity between the two atoms. If the difference in electronegativity was great enough, we would call it ionic. There are exceptions. We said if it was greater than 1.8, we would call it ionic. But it turns out that there are exceptions. And so it really is a continuum between ionic and pure covalent is really a continuum. And we can measure then the percent ionic character of any given bond. We can do that by taking the actual dipole moment, divide it by the theoretical dipole moment, and multiply it by 100. The actual dipole moments are measured by looking at those molecules and the effect of them in an electric field. And so these numbers over here are the dipole moments, the actual dipole moments that are measured for the 4 hydrohalides. We're not going to take the time to go through it, but I will point out to you that you can practice, and I'll let you do this. I've given you the answer down here. See if you can actually use that. This is the actual dipole moment for HCl. This is the bond length, and I've given you the value for Q and the definition of a Debye, and you can calculate the percent ionic character in HCl, which we actually consider a polar covalent bond. Okay, so we have 2 problems here in generating these molecules and identifying or justifying the shapes that we know that we have. If we look at these molecules closely, we can identify that the shapes we have predicted using VSEPR are correct. Those are the shapes that the molecules adopt. But we can't justify them using atomic orbitals. So we have to introduce a new theory, and valence bond theory suggests hybrid orbitals. So the 2 problems we have, the first one is geometry. If we look at, didn't need to do that. If we look at, I want to go to the pen. The electron configuration for oxygen here, this is the central atom in water. We have 1s2, 2s2, 2p4. And that's what it looks like. So if we envisioned oxygen with these two orbitals overlapping with hydrogen, which is perfectly legitimate, having a 1s orbital overlap with those two half-occupied p orbitals, we would end up with a structure that looks like this over here. We would end up with two bonds 90 degrees apart, and that's not what we have. So we have a geometry problem. If we look at the electron configuration of carbon, we have 1s2, 2s2, and 2p2. It looks like we would have two spaces to overlap here with in these two half-occupied orbitals, but what happens with the other? We have 4 hydrogens, and it doesn't make sense how we're going to overlap 4 hydrogens with this molecule. So we have an electron distribution problem, and we have a geometry problem, and we have to fix those. And so we introduced the concept of hybridization of orbitals. I will remind you that how we generated those orbitals was using a wave function. A wave function is a mathematical function that describes wave-like properties of an isolated atom. So the wave-like properties of the electron, it describes 3-dimensional space and time. So it's the probability of finding an electron in a specific region of space at a given time. And so there's 4 variables that describe psi. But these are on an isolated atom. And just because those are the lowest energy orientation for the electrons to occupy in an isolated atom doesn't necessarily mean that that's the lowest energy configuration for an atom once it enters into a bond. So in a molecule, the wave functions can combine, forming new volumes of space. And this, the property we use is the linear combination of atomic orbitals. So LCAO, or linear combination of atomic orbitals, forms new orbitals that we call hybrid orbitals. And we identify them based on the atomic orbitals that are used to make them. So an sp is a combination of the s orbital and 1 p orbital. sp2 is a combination of 1s and 2 of the p orbitals. That superscript of a 2 indicates how many of that orbital is being used. And sp3 then would combine the s orbital with all 3 of the p orbitals. Once you've done that, you've run out of p orbitals. Now, if you need to expand your octet, notice that would make 4 hybrid orbitals. If you have to expand your octet, you have to start bringing in the d orbitals. So essentially what we're doing is we're combining those orbitals and we're averaging them. So we're taking all of the orbitals that we're putting in and we're averaging them. So if it's just like taking 4 numbers. If you take 1, 2, 3, and 4, that equals 10. If you average those 4 numbers and they all equal 2.5, you still add up to 10. So let's take a look at what that process looks like. We'll start with the S and the P. An example of this would be on the beryllium atom, like BeCl2 or BeH2 or something like that. We're taking the s orbital. Let me go back to our pointer here. We're taking the s orbital and the p orbital, and we're adding them together, and we're forming 2 orbitals that have a slightly different shape. Notice that although they are bilobed, like the p orbital, they have one very large lobe and a smaller lobe. Your nuclear center is right there in the center of that. But we've created two orbitals. One of the rules on hybridization is we cannot lose any space that could be occupied by electrons. So if you are putting two orbitals in, we have to get two orbitals out. And so when you put these two orbitals together, you end up generating two orbitals that have the same look to them, but they are pointing in opposite directions. This large lobe is the lobe that is used to form the overlap. So it is going to point in the direction of the atom that it's bonding to. So again, our beryllium atom is here in the center, and one of those lobes is pointed in this direction to the left, and the other is pointing in the opposite direction, and they can overlap with a molecule or an atom on either end, and this gives us that 180-degree bond angle. Notice that on energy, our s orbital is lower energy. It contains our two starting electrons on beryllium. So we're actually raising the energy of these two electrons a little bit. This is the energy level of our hybridized orbital. We're raising the energy of those electrons a little bit, but they're not as high as the p orbitals. It doesn't represent an energy that's as high as the p orbitals. And by elevating those electrons to a slightly higher level, it allows those electron domains to get as far apart as possible. And therefore, these hybrid orbitals are the lowest energy possible for beryllium when it enters into this bond. So let's talk about the sp2. Now we're going to hybridize the s and two of the p's. We've got the px and the py here. We're mixing three orbitals together, so we have to get three orbitals out, and we do. Notice their shape is very similar to the sp orbitals, but now there are three of them, and they point in three different directions. We have them pointing at the vertices of an equilateral triangle. This would be in such as boron in the BH3 molecule. Again, we have taken the two 2s electrons and this one p electron. We're lowering the energy of the p electron, raising slightly the energy of the two s electrons, and we're creating three orbitals that are lower in energy than the p, slightly higher energy than the s, but they are overall the lowest energy orientation for this molecule. And this gives us our trigonal planar arrangement. Those three orbitals, the bonding lobe points in the direction of this equilateral triangle. When we do sp3, in this case, we're talking about CH4. That's the one we pointed out before had an electron distribution problem. Again, we're hybridizing the two 2s electrons and these two 2p electrons, lowering the energy of these two electrons, slightly raising the energy of these two electrons to generate four equivalent orbitals that are lower in energy than the p orbitals. And we generate four orbitals. They look much the same as the other hybrid orbitals, but now they point to the vertices of a tetrahedron. And that gives us the proper orientation for CH4 or for anything that has a tetrahedral shape. So when we combine orbitals to form a molecule, this is ethane, we can see that these two carbons are sp3 hybridized because they have four electron domains. Four electron domains indicate that we have to have four equivalent orbitals. And those four equivalent orbitals can point their bonding lobes towards each other here in the center to form the CC bond and the three hydrogens on each carbon to generate this structure. So the 1s orbital can overlap So you can generate that overlap using either an atomic orbital, as we showed initially, or you can generate that overlap using atomic orbital and a hybridized orbital like you can for ethane. Now that takes us to an octet. Now what happens? How do we get to the expanded octet? The expanded octet has to incorporate, we've used up all the P's, we now have to incorporate d orbitals. So you can get those using 1d orbital or 2d orbitals, and they generate the two structures we predicted before. The trigonal bipyramid is dsp3, the octahedral shape is d2sp3. Notice that there's two ways of indicating these. I say dsp3 and d2sp3. I find it more comfortable to say that. It just rolls off my tongue more conveniently. They are bonded in the order, or they hybridize in the order S first, then P, then D. So many books and people will prefer to call them sp3d2 or sp3d. It doesn't matter what you call it. If you're asked to identify the hybridization of a particular central atom, you can say it either way. It doesn't matter. Either is acceptable. So let's put it all together. When we put it all together, if you have this, notice the regions of electron density over here, 2, 3, 4, 5, 6. This is why counting electron pair geometry matters, is because you need to know the number of regions in space to determine the hybridization of that central atom. So if you have 2 regions of electron density, that has to be linear, and that's an sp hybridized. 180 degrees is your bond angle, and the molecule is linear. If you have 3 regions of electron density, you have that trigonal planar structure, looks like an equilateral triangle. That is sp2. You have to have an sp2 hybridized atom, and that gives you that 120 degree bond angle. It's going to give you a trigonal planar if they're all bonded atoms. If one of them is a lone pair, then the molecular shape is bent. If you have 4 regions of electron density, you have a tetrahedral structure. That requires sp3 hybridization, and you have the 109.5 degree bond angle. That's, if they're all bonding, that's 109.5. If you have one lone pair, such as ammonia, NH3, the nitrogen here would still be sp3 hybridized, but one of those hybridized orbitals holds a lone pair. And so the structure is a trigonal pyramid. Water would be over here. You have, again, an sp3 hybridization. 2 of them are bonding, 2 of them hold lone pairs, and that becomes a bent structure. And this is about 107 degrees. It's probably safer, rather than trying to memorize the actual bond angle, to just simply say it's less than 109.5. I say that because if one of these X's is not a hydrogen, but is some other constituent, say an CH3 or something like that, then the bond angle may change slightly. It may not be 107, but it will probably still be less than 109. So it's safer to say less than 109 there. For the water molecule, the same thing is true. When you see this as H2O, this bond angle is actually 104.5. But if that group, if one of these X's is not a hydrogen, but is a more complicated constituent, then this angle is going to be less than 109, but it's not likely to be as small as 109.5. So we like to say much less than 109 and leave it at that. Trigonal bipyramid is your 5 regions of electron density. DSP3, and again, it's a trigonal bipyramid if they're all bonding. If they're not bonding, then if you have one lone pair, remember that on this shape, it matters, and that lone pair goes in an equatorial position. This matters if you're talking about the polarity of the molecule. Notice that this structure, if we go back and think about those vectors, if these are polar bonds, they cancel each other out. The 3 equatorial vectors will end up canceling, those vectors will cancel each other out. And these 2 axial vectors will cancel each other out. So a trigonal bipyramid structure, assuming that all of those atoms attached are the same, like PCl5, that is a non-polar molecule. But if one of those is a lone pair, then these 2 equatorial electron domains do have a net dipole. The axial ones will still cancel each other out, but this molecule becomes polar. So you go from non-polar to polar. The next is if you have 2 lone pairs, that too is a polar molecule because we have axial electron domains vectors canceling, but this one has nothing to balance it out. So this is a polar molecule. Once you get back down to 3 lone pairs, however, this is, I believe, would be like an I3 minus ion, a triiodide ion. That is a non-polar molecule because there is no net vector that happens when you get this shape. So you go from non-polar to polar, 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 and back to non-polar at the end. So you have to consider 2 things in determining whether a molecule is polar or not. You have to consider the dipole of the bond, but you also have to consider the overall shape and whether the overall shape is symmetrical enough for those vectors to cancel each other out. And in our octahedron down here, D2sp3, again, this is a nonpolar molecule. It's octahedral. Once you start putting in lone pairs, this molecule is polar because there's nothing to balance out the vector that's pointing up. Once you put in the second lone pair, you now have a square planar. That is now a nonpolar molecule. So you have to look at the overall geometry of the molecule as well. Okay, I think we're going to stop there and see if there are any questions. Anything for what we've done so far?
Professor, real quick, just to clarify, the regions of electron density, the 2, 3, 4, 5, 6, that's the number of electron pairs, correct?
Yes. Yes.
Okay.
Well, let me redefine that. I don't think I would say electron pairs because that would suggest that a double bond, since you're sharing 2 pairs of electrons, is 2 electron regions. It's not.
Okay.
A double bond or a triple bond still count as only 1 region of electron density. Okay.
Okay.
So you count the regions of electron density around the central atom.
Right, not the number of bonds that are in those.
Not the number of bonds. So you count a double bond is just 1 region.
1, yeah.
There is a discussion for you to do practice on this, and I'm going to let you do that if there's no more questions. I'm going to answer questions first, and then I'm going to let you do the discussions to practice, the first discussion to practice this. I think it's on hybridization. I should double check.
I have a question on the electron configuration. So I was doing the electron configuration on an element, and I was doing the 1s, the 2s, 2p, and I got all the way to the 4d, and I put 4d2 to complete it, but it said the right answer was 5s2.
Where was this? I'm sorry. I'm not sure where.
It was one of the 4 assignments that we had due yesterday. I think it had to do with, one of the questions was with electronic configuration, and the element.
Is this Newton homework?
Yes.
Okay, if you can give me the assignment number, I can pick it. I haven't got a whole lot of experience with Newton. I have used other homework sites before and found that they are riddled with errors. And I spent the first time I used I'm trying to think, the first site that I used was I can't think of the name of it now, but I think I spent my entire first year sending them emails saying this question is wrong, this question is wrong, this question is wrong, and getting them to fix them. So if you can send me the assignment, I can try to look at it. But if you feel certain that you are right, try to take a screenshot of the question if you've got it, and I'll take a look at it.
Okay, thank you.
Any other questions on hybridization? There are 2 discussions. One of them is on molecular shape and polarity. I will set up rooms for you to work together on this. Okay, you've got 1s2, 2s2, 2p, 2s2. Yeah, okay. I'll let you guys read the chat because that may address it. I'll put you in rooms and let you work on these together. You can certainly work on these together. The point is for you to get practice, ask questions, help each other in doing this. The first is molecular shape and polarity. You must draw the Lewis structure first. Without the Lewis structure, you can't count the number of electron domains. And I've given you 2 perfect examples of that. There are 3 molecules that you are supposed to draw the Lewis structure for and determine bond angles and determine whether or not the molecule is polar based on its molecular shape. You will see that they look the same. It's very much like CO2 and H2O. You have a central atom that's bonded to the same number of atoms in both cases. One is polar, one is not, because when you consider the electron pair geometry, they have different molecular shapes. And so the first 2 are exactly like that. You cannot tell from the chemical formula. You must draw the Lewis structure. So you draw the Lewis structure, determine the bond angles, and determine the polarity of the molecules. The second discussion that I have given you is on hybridization. So I'll give you a little practice on hybridization. So I am going to give you 5 breakout rooms to work on, and I will open the rooms and you can practice working on those 2 discussions. So if you have any questions, ask them, but